Power Saving webinar. I'm Chuck Kelly, and we're going to be talking today about techniques to save power with AM broadcasting. First, I'd like to introduce my guest, Tim Hardy, the head of engineering for Nautel. Good afternoon, Tim.
Hi, Chuck. How are you?
I'm doing very well. Those of you who know Tim, they know that he's the head of engineering, and he's pretty darn passionate about AM broadcasting. But what you may not know is Tim's also pretty darn passionate about the ecology or the environment, and drives a power-saving car and has a power-saving house, and you pretty much live it, don't you, Tim?
Well, I guess I feel that there's a lot of us sharing the planet, and we should do what we can to have a small footprint. So, and you know, try to live it at home, and certainly when we're designing transmitters here, it's an opportunity to maybe even make a bigger difference than I can do at home. So we take it pretty seriously.
That's excellent. And you know, this is one of those really, really wonderful situations where doing what's right for the planet. It's also doing what's right for your own pocketbook as well.
Well, that's right. So we could, you know, again, we work hard to make the transmitters efficient, and you know, if we're getting close to 90% or 90% efficient now, and we could work incredibly hard, and we would never reach 100% efficiency. But if you look at what this technology can do, just simply by pushing a button, we can save a lot more energy with very low implementation costs. So it's a really great opportunity to do the right thing and also save a lot of money for the broadcasting.
Which is a wonderful thing. Not too many opportunities these days to cut costs further in broadcasting.
Right.
So let's punch right into it. Before we get going, though, I want to mention that this is a two-way dialogue. I can see the list of the attendees, and it's a who's who list of widely clued-in engineers from around the United States and worldwide. And so I'd like to invite each of you, as questions come to mind, go ahead and type them into the question panel on the right-hand side of your screen. And then when we get to the end of the presentation, Tim and I will go through those and, to our best ability, attempt to answer those. So please do type in your questions, and we'll do our best to answer them. So to begin, what we're talking about today is MDCL, which is modulation-dependent carrier level. It's an energy-saving technique in which the power of the transmitter's carrier signal is reduced when the audio level is low. That's really the terminology that the FCC has now used to define this new technology. And because the carrier is a major component of the RF power transmitted but really carries no information, there are substantial savings that can be had by reducing dynamically the carrier level up to 30% in total electrical costs. And the tests that have been done, and bear in mind, this is not a new technology. This has been going on for years. The tests that have been done in Europe and elsewhere indicate an undetectable effect on coverage and audio performance. And there's 5 different sub-techniques, if you will, to this overall concept of MDCL. Feel free to jump in with any questions or comments, Tim.
Yeah.
So this thing whole started out in the 80s, where they tended to have some very high-power AM transmitters in the UK and Germany and Switzerland. BBC was an early innovator. They came up with this technology to dynamically adjust the carrier level with the audio, and it's been available on Nautel transmitters since 1995. And you personally installed some of these in Europe.
Yeah, it was actually one of the first projects I worked on here. I started as an engineer in '93 at Nautel, and it was one of the first projects was to help with the implementation. And at the time, what was happening really was Nautel had the BBC as a new customer to us in some high power stations overseas, and they said, well, we'd love to buy your transmitter, but we really do need this technology in there. So it was actually driven by our customers to say we have to put this in.
Okay, and did you do any listening to it? Could you hear any difference?
I can't say I have a lot of time out in the field listening, but yeah, we did listen in the car radio and things like that going to and from the site. And honestly, you know, I think the variations you get in RF field strength out driving around are quite significant, and this is a relatively small component in those variations, so it doesn't really tend to show up.
I did have a conversation with a well-known American broadcast consultant during the IBC show, and he told me that he'd been involved in doing field strength tests and audio tests in the perimeter of the coverage, and right where it fades into the noise, and couldn't tell the difference when they would switch between one of the DCC or MDCL modes and standard full carrier. Okay, so in the United States, Tim, this was illegal, and it was illegal because of the carrier shift regulations that the FCC had.
Yep, the FCC
rules. And you gave a paper in 2009 that kind of stirred the pot a little bit.
Yeah, and Chuck Lakatos was coming to us as well, and he was paying very high energy costs in Alaska, and he'd been interested in the technology for some time. So I think also he was instrumental in getting this on the list of things to look at the FCC.
And it just makes sense. It's one of those unique situations where something that makes sense makes it through the FCC and everybody approves it, and it's a wonderful thing. So in September, just last month, the FCC basically changed its rules and said that carrier shift doesn't really make any difference as long as the reason for the carrier shift being outside the variation or the specification is that you're doing MDCL, and it's necessary for you to send a letter to the FCC requesting a waiver. The information is on your screen here. You can email also a copy to Ann Gallagher at fcc.gov, indicate which technology you're planning on using, how it will be implemented, and then they will send you a modified station license, which in effect exempts you from Part 73.1560A. So this is the mechanics of legally how you go about solving this issue. So what this technology is, again, the carrier contains more than 2/3 of the transmitted power, but it carries no information. And the challenge of all the systems, all the implementations of this technology, is to modify the transmitted waveform to reduce carrier power without reducing the received quality in receivers.
Right. So you'll see there in that slide what I've titled baseband AM signal. So important to note that this technology only affects the envelope of the signal. So you don't really need to think about the RF at all. We're not changing anything in the RF waveform like we do with the digital broadcasting. And so all these little graphs you'll see are just basically the envelope of the signal, and with one being the carrier level on the x-axis, or sorry, the y-axis. So that's just how to look at those as we move forward in the presentation.
Okay. And so one of the technologies, or one of the implementation strategies, or whatever is called DAM, Dynamic Amplitude Modulation. Would you explain what this graph means?
Yeah, so what we're showing there's actually two lines on the graph. The independent, the x-axis, is showing the modulation depth as sort of measured by a peak detector or an envelope detector in the software. And the two lines are just to show you the difference between what we're doing to voltage and what we're doing to power. So obviously the relationship there is a square law. So the lighter pink color is what's happening to the power of your transmitter, and the darker blue is what's happening to the voltage. With dynamic amplitude modulation, as with some of the others, we're only modifying the audio or the sideband component. So it's necessary that when the modulation is at 100% or higher, we return the carrier to 100% so that there's no distortion. So you see that on the right-hand side, that the carrier's gone all the way back up to 100. Mm-hmm. Actually, it looks to me, now that we're looking at it, there's a little error here because the power level would also return to 100% there. So I'm not sure. Just so everybody's clear, that is an error, but we'll fix that up later.
Okay. It's a graphical error, not an error in the system.
I think the voltage is correct, though. So
okay.
On dynamic amplitude modulation, very similar technology. The only difference now is just how the carrier level is modified with different modulation levels. And in this case, at the very low end of modulation, the carrier power is recovered slightly, and I think that's just to maybe mask, help reduce any little bit of noise at that bottom end.
Yeah, it also indicates that maybe to minimize distortion.
Yeah, although at very low power, very low mod levels, we don't need much carrier, so it shouldn't be a distortion.
Okay, and there's no change in the audio modulation, nothing changing with the carrier.
No. And really, these two things are very similar. The last line and this one are very, very similar.
Okay, DCC.
Same thing again. In fact, if we look, really, I think all we're going to see is slight differences in those points where
looks like it's a difference between 40 and 60%.
Right. So DCC is just a little bit more aggressive. So you would save slightly more energy by operating with DCC because it's going to push the carrier down to 60% to higher modulation levels. So in that 40 to 60% modulation range, the carrier level is lower with DCC.
It's actually saying that the power is down around 42% or something.
Yeah,
I'm reading that correctly.
I'm thinking I need to go through and check all the power graphs because again it's square law. So
okay.
0.6 squared is going to be 0.36. So
yep. Okay.
That's not quite right.
All right.
So okay. So now we talked at the beginning about there being sort of several different versions of this. They really fall into two categories. So all the ones that we talked about up till now, the key difference is they sort of are one of these categories where only the audio sideband is actually adjusted, and the carrier level remains. I'm sorry, only the carrier level is adjusted, and the sideband levels remain constant. Mm-hmm. In this technology, AMC, and this is the one that was pioneered by the BBC, their idea was slightly different, and the idea is that, well, what we'll do is reduce both the carrier and the modulation. And because we're reducing them together, we're going to take a different approach. At high modulation levels, reduce both together, and at low modulations, you return, at this point it would only be the carrier now, very low level modulation, return that to 100%. And the basic idea here is that when at the fringe where quality might be impaired, we'll only allow this power to be reduced when the signal is when the signal is loud so that the noise is masked. So it's a slightly different approach. And I think maybe it was because of the BBC being very, very conservative in terms of not wanting to affect audio quality in any way, where the other algorithms have a slight effect on loudness because they do adjust the ratio between the modulation and the carrier. This algorithm doesn't.
Now, all of these systems and how they sound in the field, it's going to be based on the type of modulation that you're running. Yeah. How much compression and whatnot have you got? How much heavy processing have you got? What kind are you doing? Music? Are you doing a voice? What is the type of modulation? And so really, we might look at these things and be slightly confused. Why don't you just tell us which one's the best? Well, it may be different depending on how your station is operating.
Yeah, that's right.
So it's actually useful for a station to go ahead and try the various different algorithms and see what works for them. That's right. Okay. All right. So like anything like an audio processor, there's time-domain issues, both attack and release time. Yeah. Can you explain how those work in this technology?
Yeah, the basic idea is simply that there's in the software, everything today is implemented in the DSP and software, and so there is basically a peak detector acting like a diode to detect the level of the audio, and we give it a very fast attack and a very slow decay. So the signal to move to the left on those curves is going to be slow. It's going to constantly be sort of, with peaks in audio, being pushing back to the right-hand side of the curve and then slowly releasing to the left. And that allows time for the AGC circuit in the receiver to respond to those reductions in carrier.
And you want this slow enough so that that doesn't show up as an audio artifact in the receiver as well.
That's right.
Okay. So here's some DAM waveforms.
Yeah, so again, here we're looking at the envelope, and on the top 1/3 section there you can see basically time moving from left to right, and the envelope of the audio. So this is actually spoken word. At the time it was me saying test audio. I was recording stuff on my laptop and using MATLAB. The middle graph shows the peak detector level, which would be the red, and the blue would be showing how the carrier level is responding to those peaks. So basically anywhere the blue line is reduced from 1, that's a reduction in the transmitted power. And then if you put that back into the envelope and look at the bottom 1/3, you can see what's actually being transmitted. So you can see the DC shifting of the modulation levels as the carrier is modified. But you can also see that at no time does the total level approach 0. So we're preventing any kind of distortion from occurring.
So really, graphically, taking what you just said, if I drew an imaginary line from here across to here,
right,
and then imagined all this area underneath that line, that's the power saving. That's our 30%.
That's the energy that wasn't transmitted.
Right. Okay. But you can also see just by graphically looking at it, that in terms of sideband power, that is the modulation that you see on here, as comparing to this top chart, it's not different.
It's no. The receiver is turning into audio the AC portion, not the DC. You can't hear DC, so those DC shifts have no impact on the received audio.
Okay. So here's the AMC waveforms. Similar story.
Similar story. Now, except just remember that both the carrier and the sideband are reduced together. But otherwise, it's more or less the same idea. And you might get the impression from this that maybe a little less power was saved. And I think I did sort of integrate the curves, and this one saved 23%.
Yeah.
And what did the previous slide say?
40%.
Yeah.
Okay.
So we do, typically expect that the systems that modify the carrier only do tend to be a little bit more aggressive in power saving.
Now, that having been said, you were running a mic directly into your notebook.
Yes.
You were not having an audio processor, so those differences might be somewhat mitigated.
Right.
Okay. And then there's the DAM block diagram.
Yeah. Again, this is how an approximation of what the software does, just to give you a sense that we're detecting the peak, and we're looking at, there's a lookup table that has to somehow determine what the carrier level is adjusted by. But it's maybe less important. It's all done in software, and it's been checked out already.
Okay, and the AMC?
Same thing.
Yep. Okay, and now all of the transmitters, both the ones we currently manufacture, say the NX, but other transmitters that Nautel manufactures or has manufactured, when we modify them for MDCL, we utilize this card.
That's right. So this card was developed for NX. It was a big part of the NX project, and it was the first time we had an exciter for AM transmitters that was based on digital signal processing. And because of that, it makes it relatively easy to implement these types of things. And it's part of how we get the best possible performance with NX. So when we wanted to go back and implement these on the older transmitters, we actually did have another system, but it was developed in 1995 and was getting a bit old. So we basically just took this card, we put it in a one-rack unit box that will show. It has the user interface and has the proper connections to an older transmitter.
And it's basically connected up the same way you would connect a Sequom exciter or something like that.
That's right. It's even simpler than that because we don't actually need the phase. As I was saying before, this is entirely envelope processing.
Yeah.
So this box would have a phase output, but you don't need it. That's just there if it were used for HD radio or Sequom or something.
Now the other thing we can mention here is in the NX series, this stuff works today.
Yeah.
But that in November or so, we are introducing new software which will also allow you not only to select through the 5 different systems of MDCL that we support, but also to adjust the amount of effect so that if you want to turn it up until it hurts, you can.
Yeah.
And save a whole bunch of money.
That's right. Yeah. So it's just basically you can imagine all of those curves can be scaled, and the hooks are going to be in place in the new software release to basically turn these on at a very low setting. If you're being very cautious and want to listen to the differences very carefully, and then over time you can adjust the level until you're happy with the compromise.
Okay. So let's talk about what's possible, and this is the part you want to show your general manager before you go looking at doing this, because it is possible to save a pretty healthy chunk of change with this technology.
Yeah.
It's most relevant to medium and high power stations that is 10 kilowatts and up. You're not going to save a fortune if you do it on a 1 kilowatt transmitter.
Right.
But it also is important to remember that this technology is in addition to whatever savings you've got due to the efficiency of your transmitter.
Yeah.
So when we look at this, most of the state-of-the-art AM transmitters are roughly 90% efficient, and that is ours are.
Yeah.
And the assumptions and calculations, the average power consumption of a 50 kilowatt transmitter, these assumptions are all at 50, based on 73 kilowatts, 70% average modulation, which is 8,760 hours per year. That's a 24-hour, 365 station.
Right.
640 kilowatt hours per year.
640,000. Those are actually 640 megawatt hours.
Yeah.
Yeah.
Electrical rates can range from 5 to 20 cents per kilowatt hour, depending on the region. And if you're using one of our high efficiency NX series transmitters, you might expect if you're paying 10 cents per kilowatt hour to save over $19,000 a year.
Right.
And if you're running 15 cents per kilowatt hour, you're looking at somewhere around $28,000 a year.
Yeah.
Now, if you're using an older plate modulated transmitter, which may be 70% efficient or something, and you change your transmitter to one of these new transmitters and implement MDCL, you're looking at saving $37,600 per year, or up to $56,000 at a higher kilowatt hour rate. Now, remember, the other thing that's interesting about this is that these these numbers are only accurate if the energy costs stay where they are. But if recent history is of any consequence, they don't. They're going up.
Right.
And the savings would go up.
Absolutely. It's a compounding interest kind of thing.
Precisely. Okay, so let's talk about perceived quality. There have been a number of tests. There's a lot of people that believe you don't get something for nothing.
Right.
So they're looking for the downside. And there were a lot of tests not only in the laboratory but also in the field, both here but also a lot of them in Europe where the technology was originally developed. And basically the bottom line is people could not tell the difference. People could not hear a reduction in coverage area, nor could they hear an increase in either distortion nor signal-to-noise, a reduction in signal-to-noise performance. Tim, one question that just occurred to me, and sorry about this, but what happens in the case of a synchronous detector? If you happen to have one of those fancy radios that uses a synchronous detector?
It shouldn't matter. I mean, the synchronous detector is, primarily you're talking like a Sequan receiver or something.
But there are.
I wouldn't expect it to be any different, honestly.
I wouldn't either. Yeah. Okay, so with regard to audio processing, as you get to more and more heavily compressed audio, as you approach square waves of 100% modulation, there's less benefit to this technology. However, voice programs, or when you're using voice, it tends to be very, very powerful.
Yeah, voice is really good. I think what happens if you're running very loud music, heavily processed, that the peak detector is going to sort of hang at the right-hand side of the curve, and it's almost as if you had just turned the power down a little bit.
Sure. Okay, so let's talk about what happens if we go to HD radio and enable this technology.
Right. So there's been some discussion about this for some time, and the first question is how hard is it to actually implement? Because with HD radio, there's certain aspects of the transmitter actually kind of move out of our exciter into the HD radio end of things where we have software from Ubiquiti. But we were able, Brian Walker, who's actually here with us right now, he was able to figure out a way that that problem could be fixed, and that basically the carrier that comes from the Ubiquiti system basically needs to be filtered out and then reinserted, and we, of course, need to modify that level. So he was able to get that to work, and we did some initial testing in the lab. And certainly the signal can be put on the air with an HD radio implementation. The software that's in the current release of the NX products isn't quite there, but this release that we're coming out with in the next couple of months will support this. The one caveat that we have is that the HD radio, there are many people who are broadcasting HD radio on AM hybrid, and there are many of these stations do struggle with spectrum compliance. And the advantage that AM has with HD radio is that the carrier level that's present in a hybrid signal has the effect of basically making the signal easier to amplify in the linear amplifier, in the transmitter. And when we reduce that carrier level, it increases the bandwidth of the magnitude and phase signals passing through the different parts of the transmitter, the modulator and amplifier. And when those levels, when the bandwidths are increased, it becomes more difficult to stay within the mask. So if you're implementing this with HD radio, you just need to be a little bit cautious that you should probably turn it up slowly and verify that it's not causing you a spectrum mask compliance problem.
There's not a large body of experience yet in this.
No, and I think the other thing we did find, I do tend to recommend, at least personally, the AMC as the starting point, and we did find that AMC performed better in this respect.
Okay. Let me ask you a question. I'm just trying to understand all the things you just said about,
yeah.
And to me it sounds as though it's analogous to the PAPR discussions on the FM side.
Similar, yeah.
So when we reduce the FM carrier, or we increase the digital carrier's ratio to the FM carrier,
yeah.
the need for linearity in the transmitter is increased in order to make sure we have spectral mass compliance, and similar to this situation, because we're getting rid of that non-changing,
yeah.
almost biasing component.
Yeah, it's a similar situation.
Okay. Good. All right, so in the NX, I go back to Dorothy in The Wizard of Oz, in the ruby slippers. It's already there. You know, There's no place like home. You know? It's already inside the transmitter.
Right.
Every NX transmitter we've shipped has it already in there. You just need to turn it on.
Right. Just press the button.
And the reason for that is, and I'll go back to a discussion you and I had, Tim, some 3 years ago, where we looked at the possibilities for including MDCL, or DCC as we called it at that time, in the transmitter. And from the sales side, I was sitting there saying, okay, well, this is what most people charge, somewhere between $3,000 and $4,000 or $3,000 and $5,000 for this. So we'll software enable this feature and let people buy it. And you were rather adamant about the fact that no, in the NX series transmitter, it was going to be free because it's the right thing to do.
Absolutely. As we said, it is the right thing to do. I mean, this is why we were hoping to get this to start to happen in the U.S. It's a great opportunity.
Okay. So right built into the NX is the ability to select the 5 algorithms, and we'll be able to show that on the AUI, because we're going to go to that live in here in a minute.
Right.
So this is the AUI. This is what you see on an NX series transmitter, and this is how you pull down that on the AUI and select one of these modes. So this is within the presets menu, and you can select any of these implementations of that as well. So now let's go and see if we can go to the live unit, which is sitting down in our test lab at this point in time, and I will let you drive, Tim.
Sure.
There is the AUI.
So with everything set up right here, we just need to turn the transmitter on, and it's currently set up just to run regular AM.
Okay.
And what we have is a CD player playing out some processed AM content, and I think it's primarily voice, so it's like a talk radio. And we actually one of our customers helped us out with this content, so they actually captured some real broadcast material that we're running right now. And you can see that the peak levels are fairly good. We've got negative peaks about 94%, positive peaks up to 120 or 125%. Nice things about NX here is you can look at this one's it's a 50 and it's running at 10 kilowatts. Just a limitation in the load we have right now, but so the PDM is relatively low duty cycles. But you can monitor when you're doing this. You don't actually have to wait, especially with NX. You don't have to wait until you get your power bill 2 months from now. You can look at right here. This meter will tell you right away. The DSP is actually measuring the total average power, the RMS power that's being transmitted. And when you turn on the carrier control, you'll see that meter change. So that's the key one to watch. And it should directly project the difference that you would expect to see in your power bill. So if I go, we'll just go and turn it on now. We go into presets. So it's going to pull up current settings. We can see we're in analog AM mode. And let's see, dynamic carrier control right here. All we have to do is choose a mode. We'll go with AMC first and just click activate. And right away you see the power on the top is dropped. So where normally the transmitter shows all the time 10 kilowatts, you're going to have to get used to walking up to your transmitter and it's saying somewhere between 5 and 10 kilowatts.
But again, the listener at this point in time
shouldn't have noticed a difference.
Wouldn't have heard a difference.
Right. And look at the RMS power now. We were up around 11 kilowatts before. Mm-hmm. So it's pretty dramatic. You can see, I mean, that's definitely going to show up on your power bill in a big way.
Yep.
I don't know what else I can show. So we can go in again and we can choose one of the other modes, menu, presets. We'll switch to DCC or DAM, how's that? DAM, activate, close that window. There you go.
Yep.
Hard to tell the difference from the front panel, but they're both running. You know, you could look. You know, if you're really interested in the detail, probably interesting to look with an oscilloscope. Just look at the mod monitor, you know, the RF monitor point somewhere, and you'll be able to see quite easily on an oscilloscope.
That brings up an interesting question. Does the mod monitor in the station act any differently?
Yeah, it will. It will. That's something you're going to have to look into. Is you know, if you have a carrier alarm, there's no question that the carrier alarm is going to go on your mod monitor.
Okay, but what about the regular modulation numbers? Can you still believe the modulation number according to the mod monitor?
No, it's quite difficult because the, at least in my experience with the mod monitors we have here, they respond differently than a receiver in that they are trying to measure the carrier very accurately. So they have very long time constants on the carrier measurement.
Yep.
And when they show you the mod depth, it's going to show you something that's not right. It's certainly going to show you, you know, the carrier is obviously moving. It's going to show you that. But I'm pretty sure the mod depth is off. And, you know, in reality, the mod depth actually is off because depending on which algorithm you're running, you are affecting the modulation depth.
Yeah. So if you would recommend that the broadcaster set his modulation levels using the indicator on the transmitter.
That's right. And, you know, we even talked about this briefly with the FCC saying, you know, if broadcasters are going to operate with this, when they go and make these kinds of checks, which might depend on a fairly constant carrier level, it's, you know, the simplest thing is just shut it off while you're making those checks and then turn it back on again when you're.
Well, that was specifically, if I understood it, when you're running your radials and you're checking the coverage of the station, or the field strength at various points, you've got to turn off MDCL during that time, otherwise your meter is going to read lower levels.
Right.
Okay. Anything more you'd like to do here?
No.
Okay.
That's it.
All righty. So let's go back to the screen and continue on. Okay, so the idea in terms of implementation of MDCL on Nautel transmitters is that on the NX it's built in, it's automatically there. On the XR it's plug and play. You simply buy this new MDCL exciter. It costs less than $5,000. And on the XL, the ND, the NA, and the J1000, there are other minor modifications that are necessary.
It's fairly simple to understand. Actually, the later model XLs should also be plug and play sometime after maybe 2001. And the modifications we're making are the same as the modifications we make on older transmitters for HD radio, with the exception we don't need anything for the phase component. It's just basically you need a DC coupled. You know, you could almost do this sort of thing yourself if you're interested in trying, but what you need basically is the audio input to be DC coupled, because we're going to feed the carrier along with the audio into the audio input of the transmitter. And where it would normally insert the carrier as a separate, you know, in the exciter, that needs to be set to 0 because the carrier is going to come in through that DC audio input. And that's it. It's a fairly minor modification.
Okay. And again, customer service at Nautel can help you with this.
Right.
So summarizing all the things we just talked about, it's a proven approach, MDCL is, dating to the 1980s. It can cause or create savings up to 30% in your overall power bill. It has minimal, and some would say undetectable, impact on the received signal. It has very low implementation cost. It's been used for years outside of the United States, and it's now permitted here. And for Nautel customers, it's standard and free, thanks to Tim, 90% efficient NX series, and it's a 1 RU exciter upgrade for less than $5,000 available for our other AM transmitter series. So here's where you can go for more information, the Nautel Waves newsletter, the webinars. Bear in mind that next week we've got another webinar where we're going to talk about the new NX features. Next week, same time, same place. And we have a YouTube channel and a Nautel store, all of which are interesting. Now, I'd like to go ahead and see if there are any questions that we've come up with, and it doesn't. Wait a second. I take that back. There are some here. Let me see here. Okay, let's see here. Wow, there's a lot, as a matter of fact. Let me see if I can figure out how to make it a little easier to see. All right. Okay, it says sound is good. 90% efficiency is AC to RF or PA input. It's AC to RF.
On an NX, the high power NX, it's AC to RF.
Thanks to Paul for that question. Right, so one person has indicated that the FCC has explained to them that they want them to indicate the make and the model of the transmitter and information on the device used to implement MDCL in the letter. We mentioned that as how it's implemented.
I think it's only approved for Harris and Nautel transmitters.
I believe that's those people that have responded saying that they've got this technology at this point in time. Okay, and let's see here. Can the transmitter be switched to a non-suppressed carrier mode for typical field measurements, i.e. AM antenna, proof of performance? Interesting point. One of the things you could do with the NX, because of the presets, the way the presets are configured, you could have two presets configured absolutely identically, except the only thing that's changing is whether or not you're enabling MDCL. So you could even remotely turn MDCL on and off.
Yeah, so in any implementation, it's as easy as pushing a button, and it could be remoted as well.
Okay, and there's somebody saying, yes, we have to manage the issue with the modulation monitors because program directors are highly sensitive to that. How is the MDCL used with an XR50 and an NE-IBOC exciter?
Right, so we touched on that. There is a software upgrade that's going to be required. We're going to have, actually at this time nobody's on the air that I know of. We're certainly talking to a couple of broadcasters right now about getting this HD radio and MDCL on the air in the next potentially few weeks. And the other thing is that the new software that's coming out will make it easier.
Okay. There's also another question. What about the AM-IBOC exciter? Since that's basically the same thing as what we're talking about, is they don't need an extra box at that point in time.
Right, provided they mean the most recent 1RU AM-IBOC exciter.
Right,
it will support.
Not the NE-IBOC, that's right. Okay, so those are the questions, and I thank everybody who asked questions, and we press on. So if you have further questions, you can email us either at sales@nautel.com or to any of the regional sales managers that you work with, and we'd be very pleased to hear from anybody, and we want to thank you for being here. And Tim, any final parting thoughts?
No, thank you very much, and I hope that people make an effort to put this on the air.
This is wonderful technology. Thanks so much for joining us, and bye for now.